So for this video, part 3, we're going to be going over our resting membrane potential, our cell membrane, and then also the size of our resting membrane. So to start out, what is resting membrane potential? So you have a cell, okay? Got a cell. I kind of talked about this in later videos, but it's okay. So you have a cell, and there's going to be some channels in the cell. There's a couple of them. We'll just do 3 for now. Now we'll just do 2, okay? So one of these channels, okay, whoa, pause. All right. First, we're gonna talk about the constant, or the ions that we're dealing with. We're dealing with potassium, and we're dealing with sodium. Those are what are important for this conversation. So, the first thing to establish is what are the concentrations like compared to inside the cell, outside the cell. So potassium is super high inside the cell and itty bitty outside the cell. Sodium is high outside the cell and itty bitty inside the cell. So you have this first channel, which is known as your potassium leak channel. And potassium wants to rush out. That's what it's doing, is it's going to rush out, and as these positive charges leave, it's going to leave a slightly negative charge or polarization inside the cell, right? You have positive ions leaving, so the inside the cell is going to get more negative, okay? But you do have other ions that are in here, right? You have your hydrogen, you might have some calcium, okay? And so those charges are going to kind of negate how negative it can get, right? As well as the want for some of the sodium to come in, right? And so if this is a neuron, we're going to call this our resting membrane potential, or RMP. Okay, so we're going to go over to our little graph. So for a neuron, our resting membrane potential is -70. That's our RMP. This is what your cell is at rest. It's before different ions go in and you get a graded potential. It's before the depolarization and hyperpolarization. It's just your cell at rest. Okay, that's what your RMP is representing. Can I turn this on? Okay, well, whoops. Okay, so that's what your RMP is representing, is what is the charge at rest, right? And this charge is going to be our -70. And that is established because this potassium is leaking out. Okay, whereas our sodium wants to come in, you have other charges, and so that's why it's not quite so low, as well as saturation, the amount of channels that you do have available for the potassium to leave. All of that is going to contribute to that -70, which is the characteristics of our cell membrane, right? Our cell membrane right now is permeable to potassium, but not permeable to sodium. If it was permeable to sodium, right, then we'd start to have that depolarization. But at rest, right, the resting membrane, at rest, we're not permeable to sodium, we're only permeable to potassium, okay? And then there's this thing called magnitude. Basically what that means is, like, where is resting membrane potential? Is it at -70? Is it at -90, like your heart cells? Is it higher than that, right? And so that leads us into something called our Nernst equation. I don't know why I'm drawing a line. Okay, so our Nernst. Our Nernst is equal to -61.5 over Z times the log of the concentration inside your cell versus the concentration outside of your cell. And the Nernst assumes 100% permeability. Okay, Nernst is 100% permeability for this to work. Okay, and so potassium's permeability, with its typical concentration in the neuron, our Nernst is -94. That is how low it wants to bring us down. Okay, so way down here is where our potassium would like us to go. Okay, and so that is called your driving force. Okay, so that right there, that difference is your driving force. So there's an equation. So your driving force, because there's a couple different factors, right? You've got it, the concentration, it's positive inside, is a large concentration in here, a smaller concentration out here, right? So that's the concentration, that's one factor. But another factor is electrically. If it is more negative in here, that positive should be attracted to it, right? So this driving force is going to tell you what is the ion actually going to do. When it is compared, when it's faced with an electrical drive and a gradient drive, what is it going to do? So your driving force is the voltage of the membrane minus your E, which is your Nernst. Okay, so let's take potassium. Voltage of the membrane, by the way, does not always mean resting membrane potential. It could be anywhere along this graph right here. Okay, so let's start with, we'll just say we're at like, I don't know, let's say we're at 35. No, we'll do 50. We're at negative 50. Okay, so we're at this negative 50. So what you're going to do is you're just going to plug this into the Nernst equation, or you're going to use that with the Nernst and do the driving force. So it's going to be negative 50 minus negative 94, which is going to equal your positive 44. Okay, and so what you're going to do is then you're going to take that and you're going to put that number inside the cell. Okay, so this is a positive 44. Okay, and so this is a positive, and your potassium, the one that we're using for this equation, is also positive, right? And positive forces don't want to be next to each other, so that is the way that it's going to go. Even though there may be some electrical, right, because you're still negative, you're at this negative 50, overall the driving force is enough that this potassium is going to leave. And it varies on different places of the membrane. Lots of times I like to just visualize it. So at negative 50, whoopsies, at negative 50, there is a higher driving force for potassium leaving than there is at negative 70, right? Because you can just kind of visualize that. But for sodium, which we'll do in this color, but for sodium, there's a very big driving force, right? For sodium at negative 70, but there's less of a driving force at negative 50. So sometimes you can just visualize where you're at and then move and adjust accordingly, right? Because for sodium, we kind of have a hard rule that sodium always wants to go in, and that's because its Nernst is trying to get you up here to like positive 55. It's always trying to bring you up to that. It's always trying to depolarize and bring you higher. So that's pretty much why it's always going to go into the cells, because it's trying to bring it up higher. So that is how we get our resting membrane potential, is through this potassium leaving through the leak channel, establishing that resting membrane, leaving behind that kind of negative polarization. It's because the cell membrane is only permeable to potassium right there, and not sodium, which is what makes it want to go in. The size of it, the magnitude of it, is referring to it going down to like negative 90 or negative 70, because again, it is different in different places, right? Neurons negative 70, heart's negative 90, and it has to do with that driving force of potassium always wanting to really drive you down to the negatives. And then that's also our Nernst driving force. So that's the end of this first video.